So let's look at different IV curve, and I'm going to explain the slope and chord conductance. So we know that the conductance is the slope because this is IV curve. So we're talking slope, rise over run, I over V, and the I over V, because V is equal to IR, is 1 over R, and 1 over R, 1 over resistance, so it's conductance. Okay, so coming back, but now we're going to define this conductance, so that called chord conductance. So that is a slope conductance, which is what we're used to. It's just like we're taking derivative, and then there's like tangent line, bam, 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 and then there's like the slope. That's a slope. But however, we're talking chord conductance, and what it is so if you want to know the slope of here or the conductance, what we're doing, instead of taking just like vertical tangent line here, we're actually drawing a line that's connecting these two dots, where this one is our point of interest, but this is the membrane, the Nernst equilibrium potential. And why it matters is, I'll explain. So when we talk about this, like the change in the membrane voltage, what really matters is like how much it deviated from is like stable state, the resting state, the stable state, so our Nernst equilibrium potential, right? So if the equilibrium potential is like negative 80 millivolt, and then it becomes like, let's say like negative 20, so that's like then this is like 60 millivolt like changes. And then maybe we can move to like, actually, it doesn't matter. I think you guys will understand. So like, what matters is how much it deviates from its resting state. So instead of 0, we're talking from like here. So because we're measuring the deviation from is like stable state, Nernst equilibrium potential, the voltage of for the point of our interest over here, let's say like 10 or something. And so 10 will go here, and then negative 80 will go here. And we will get this deviation. And then I over here is just current. So and we're drawing this triangle. So this is I, this is the V minus EC going over here. So we got this nice triangle going. And that is the slope, the chord conductance, right? The slope of this thing. And so that is what's more commonly used in electrophysiology. And the reason why is like sitting it here in Nernst equilibrium potential, because Nernst equilibrium potential measures steady state. And when it's steady state, it means like after a very long time, it converges into like some values, for in this example, negative 80. And that means the the amount of current or the amount of ion that's going through the membrane at that is 0, which is why it's sitting at here in this line. If it were non-zero value of the current, that means for infinite amount of time, that a certain number of ions is going through, and then that means that like the cells will either shrink because all the ions are like, got out of the cells, or it will burst because the certain amount of ions coming in like infinitely. So that's why it's sitting at like this V line. So that's the chord conductance. So knowing this, what we can do is we can measure. So for here, we went from VI curve to conductance. We're going to go the other way. So knowing chord conductance, can we draw the VI curve or IV curve? So let's say we have this, so some voltage value here, and then this is V, this is conductance, and then so at this voltage it was this, but it like changes like a step function like, and this is V, this is I. So what would happen? It will have certain conductance, right? There's certain low conductance. Actually, I'm gonna draw it slower, lower. Okay, but at this stage, when it reaches 0, it's gonna shoot up But so we may expect it to go like this way, right? Boom, 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 increase in slope. But that's for just regular slope conductance. For chord conductance, it's about connecting the line between this Nernst equilibrium potential and then the line and then the slope that forms between the lines. That's what matters. So what has to happen is it has to jump like that, and that will allow us to draw a new line that connects these 2 points. And they will have different slope. This line will have different slope or the different chord conductance than this one. So that explains why this kind of funky looking thing is happening, this jump. And for the E2, so it has a high slope or high conductance, right? And then so E2 going like fairly high slope, and then it has to come down a little bit, jump down, right? So now the line that connects these two, it's not quite a straight line, but you can see that this has a lot smaller slope than this line. So there's that.